Hello everyone, welcome to my YouTube channel. In this video, I will be presenting my macro engineering course project. So in this project, I designed an RF amplifier in 1.5 to 2 GHz, and I will be talking about RF amplifier design steps, generating its layout, and for the last part, I will be talking about assembly and characterization. So for this project, I used a single voltage supply and matched its output and input ports to 50 ohm so that it has better return loss than 12 dB. And it is unconditionally stable with a gain of 10 dB and gain variation is also smaller than 0.5 dB minus and plus. To complete this project, I used a single stage amplifier with transistor BFP196WN. So here is my design amplifier. As you can see here, I placed a stability network, biasing network, and DC block capacitors, input and output matching, also transistor. So at this point, I would like to talk about beta dependency of the transistor. By giving a negative feedback from collector to base through the biasing network, I was able to reduce my beta dependency of the circuit so that variation of the transistor parameters would affect my circuit less and less. Also, I placed two capacitors to input and output port to give some tunability. So, as I mentioned earlier, I had some requirements, and within my simulation, I am able to meet them all. I have stability for whole frequency range, a good S21, which is gain, and good S21 and S22 better than 12 dB. But to achieve this, I used maximum available gain method. I am trying to match my circuit for 1.5 GHz for the best gain, and by putting some losses for the smaller frequencies, I was able to meet all the requirements. But in order to physically realize my circuit, I had to change some components. First, I changed resistor, capacitor, and inductor values with the available market components. Then I replaced transmission line with the proper ones for our fabrication process. After that step, I was still able to meet the requirements. Also, my gain fluctuation and stability factor went better. So here's my layout. As I mentioned earlier, I have two components to tune my circuit. After fabrication, there may be some variation, some errors, even some components may not be at the value that they tell. So at that point, I have to tune my circuit properly so that my amplifier works as I desire. At the input port, I placed a capacitor which place can be changed by soldering and resoldering. Also at the output port, I place an open circuit transmission line where I can add and cut some wires to change this capacitance seam from this transmission line. So after fabricating the PCB, I assembled the components. As you can see here, here's input and output port with ground, cable, and supply cable. So I also put some wires, then solder them properly to give ground feedback from backside of the PCB to front side. So here's my S parameter measurement result. As I mentioned earlier, I had two tuning components. By tuning them together, I was able to get gain for some value. But at the beginning, I didn't have much gain, but tuning was an essential step for me to have some gain, have some stability for my network to make my circuit behave like an amplifier. And although I weren't able to meet all the requirements, I had some gain and good S11 and S22 for some range. So In order to characterize my circuit, we define P1 dB point, which is actually the output power level where input power level is driven so high and our amplifier compresses its output power. So at that point, we use our network analyzer and preamplifier with an attenuator. You may ask why you did that. Because our network analyzer were not able to supply enough input power so that our amplifier get compressed. Also, in order to protect our network analyzer from high power, we placed an attenuator at the output side. With this circuit, we was able to observe P1 dB point. So for 3 different frequencies, I made some measurement and here's the result. For 1.5 gigahertz, I have 0.3 watts. For 1.75 gigahertz, I have 0.5 watt. For 2 gigahertz, I have 0.77 watts, 1 dB point as an output power. In order to get this result, first I made a measurement for the linear region. Then after getting its gain, I find a value below 1 dB for this level, then find the output power by adding the attenuation, which is attenuated at the output side of my amplifier. Another important characterization method is IP3 measurement. Since amplifiers are nonlinear devices, when we supply 2 different signals from 2 different frequencies, they generate harmonics. So the most important harmonics are third harmonics because they are really close to fundamental frequency and they might destroy the signals. So in order to have this property and characterize it, we made IP3 measurement. In order to do so, I made a measurement setup, which is amplifier is fed by 2 different frequency sources. In this case, I supply them with 1.750 megahertz and 1.751 megahertz. Then, after giving the combined signal to amplifier, also which has the same amount of power, I was able to observe third harmonics. Here, we can see fundamental and third harmonics. As you can see over there, there is our fundamental amplified signals and third harmonics. So my power level at the fundamental frequency is minus 10.1 dBm. And for the third harmonic, it's minus 81.5 dBm. And also knowing the fact that the third harmonics increases by 3 dB, where our fundamental frequency increases with 1 dB, we are able to estimate IP3 points. So for the output power IP3 point, this 25.495 dBm. And another and one of the most important characterization method of an amplifier is noise measurement. So if we are designing a low noise amplifier, we want our amplifier to have a low noise. To characterize my device with the noise figure method and noise source, I construct the given measurement setup. And after calibrating my noise source with the noise figure meter, I was able to observe the noise. But if device using hot and cold mode, it is able to extract information which is noise added by the amplifier. So by using that, I found that I have 2.33 dB noise figure at 1550 megahertz. So as a conclusion, I learned how to design an RF amplifier, fabricate and assemble it, and how to characterize it, and what's the most important characteristic of an amplifier when we want to use them for RF systems. Thank you for your interest. I would like to have your like and comments below.